Metallurgy. Metallurgy constitutes the scientific and technological process used for separating metals from their ores. Ores are naturally occurring materials from which the metal can be extracted profitably. Elements may occur either in the free state or as part of a compound. In compounds, the nonmetals are found usually in the reduced form and the metals in the oxidized form. Most metals, except for the unreactive ones such as gold and platinum, occur as compounds known as minerals. Minerals are the naturally occurring chemical substances in the Earth's crust and are obtained by mining. These are associated with earthly materials known as gangue. Gangue contains ores. Except for the most unreactive ones, metals are extracted from their ores by reduction processes. Before the ore is subject to reduction, it has to be subjected to various processes such as concentration, roasting, and smelting. The entire process happens in stages. The 3 stages of metallurgy are concentration of the ore, extraction of crude metal from the concentrated ore, and refining of the crude metal. Concentration of ores. Different methods of concentrating ores are available. The choice is based on the type of impurity present, type of the metal, and the facility. The process of removal of unwanted earthly materials, gangue, from the ore is called concentration, dressing, or benefaction. Before the ore can be concentrated, it must be graded, pulverized, and ground to a powder. Then the ore is concentrated through one of the following processes: hydraulic washing, magnetic separation, froth flotation, or leaching. Hydraulic washing makes use of the difference in specific gravity of the ore and the gangue particles. It can also be known as gravity separation. The water stream will remove the lighter gangue particles, leaving the heavy metal ore particles behind. Magnetic separation takes advantage of the magnetic properties of some metals. The crushed ore is passed over a belt, which then passes through a magnetic roller. The particles attracted by the magnetic rollers form a separate pile from the gangue particles. The magnetic separation is used for separating tungsten particles from cassiterite, which is tin ore. It is also used for separating out iron oxide as well. Froth flotation is a useful technique for separating sulfide ores of zinc, copper, and lead from the earthy contaminants. The main principle behind froth flotation is the ore has an increased wetting ability of the mineral particles over the earthy impurities. This difference allows the ore to be separated from the gangue. First, the powdered ore is suspended in water. Collectors such as pine oil, xanthate, and fatty acids, which enhance the wet ability of the mineral particles, are added to the suspension. Froth stabilizers such as creosoles and aniline are added to increase and stabilize the froth. The froth is skimmed off, allowed to collapse, and dry before recovering mineral particles. Froth flotation also provides a way of separating different sulfide ores by adjusting the proportion of oil to water in the mixture. Leaching is useful if the ore is soluble in a suitable solvent. In the Bayer's process, the bauxite ore is concentrated using a solution of sodium hydroxide, which dissolves the aluminum oxide, leaving the impurities behind. Leaching is also used for concentrating some gold and silver ores. Extraction of metal from the ore. The concentrated ore must be converted to a form which is suitable for reduction. If the ore is a hydroxide, carbonate, or sulfide, it is subjected to calcination or roasting/smelting to form the oxide. The concentrated hydroxide ore is subjected to heating in a regular supply of air where the volatile matter is burnt away and the oxide of the material is obtained. Sulfide ores are roasted or heated in presence of regular supply of air at a temperature below the melting point of the metal, where it will be converted to oxide or sulfate. A reverberatory furnace is usually employed for calcination and roasting. The roasted oxide or sulfide of the metal is now subjected to reduction. It can be done by one of the methods listed below: chemical reduction, auto reduction, displacement reaction, or electrolytic reduction. Chemical reduction. There are several different methods of chemical reduction depending on the reducing agent. 1. Carbon as a reducing agent. Carbon, in the form of coke, coal, or charcoal, reduces many metal oxides into the respective metals. The following reactions provide a few examples. You can see the oxides of metals like tin, zinc, or different ions of iron reacting with some form of carbon to produce the respective metal: tin, zinc, iron. 2. Hydrogen as a reducing agent. Because of hydrogen's flammable nature, it is used in very few cases. When used, it works according to the following reaction, where you have some metal oxide reacting with hydrogen to produce the metal and water, where M is either tungsten or molybdenum. 3. Aluminum as a reducing agent. The oxides of chromium and manganese are reduced by aluminum by aluminothermic reduction process or Goldschmidt thermic process, according to the reactions below. You can see the reaction between a chromium oxide or a manganese oxide with aluminum to produce the aluminum oxide and the metal chromium or manganese. And 4 other metals. Sodium and magnesium metals can also be used in certain cases for chemical reduction. Other methods of reduction. Auto reduction. When no reducing agent is necessary, the metal is obtained either by simply roasting or by reduction of its partially oxidized form. Displacement method. Some metals are reduced by displacement with a more reactive metal. Gold and silver are obtained from their complex cyanides when more reactive zinc metal displaces them. Electrolytic reduction. Highly electropositive elements in the first and second group are reduced using this method. When electric current is passed through the fused chloride of these metals, metal ions are discharged at the negative cathode and deposited. Refining of the crude metal. Metals extracted by any of the above methods described in the previous slides are usually contaminated with impurities. Various methods of refining are employed depending on the nature of the metal and impurity as listed below: distillation, liquation, electrolysis, zone refining, vapor phase refining, chromatographic method. 1. Distillation. This is useful for low boiling metals, for example, zinc and mercury. 2. Liquation. A low melting metal like tin can be made to flow on a sloping surface and thus separated from the higher melting impurities. Electrolysis. This method is widely used in the refining of copper, gold, silver, lead, zinc, aluminum, etc. The impure metal is made the anode, and a pure strip of the same metal is made the cathode, and is kept in a suitable electrolysis bath made up of a metal salt. When current passes through the electrolyte, pure metal from the anode dissolves in the electrolyte and is deposited at the cathode. A high voltage is applied to keep the impurity, a high electropositive metal, as ions in the bath, whereas the less electropositive metals, the impurities, remain ionized and fall down in what is known as anode mud. Thus, copper can be separated from the impurities, while zinc would remain in the solution, and less basic silver and gold would go to anode mud. 4. Zone refining. This method is used when metals of very high purity are needed. Zone refining is based on the principle that the impurities are more soluble than the pure metal. A circular mobile heater is fixed at the end of a rod of impure metal. The heater is moved forward and the melted zone moves along with the heater. As the heater moves forward, the pure metal crystallizes out of the melt while the impurities pass into the adjacent molten zone. The process is repeated several times until the desired purity level is reached. The end of the rod where the impurities get concentrated is finally cut off. Semiconductor metals such as germanium, silicon, boron, gallium, and indium are purified by this method. 5. Vapor phase refining. Mond and Van Arkel are the two main vapor phase processes in use. In the Mond process, nickel, when heated in a stream of carbon monoxide, forms a volatile nickel carbonyl. This vapor, when subjected to high temperature heating, undergoes thermal decomposition, giving the pure metal. In the Van Arkel process, zirconium or titanium is heated with iodine vapor at about 870 Kelvin to form volatile zirconium iodide. The latter, when heated over a tungsten filament at 2100 Kelvin, decomposes to give pure zirconium. 6. Chromatographic method. The principle of separation or purification by chromatography is that various components of a mixture are differently adsorbed on an adsorbent. In column chromatography, an adsorbent, such as aluminum oxide, is packed in a glass column. The mixture to be separated is taken in a suitable solvent and applied from the top of the column. The components in the mixture get adsorbed in the column and are then eluted out using a suitable eluent or solvent. The weakly adsorbed component is eluted first, followed by the more strongly adsorbed ones. This method is suitable for such elements which are available only in minute quantities and have chemical behavior not much different from the metal to be purified.